Hi, I'm Nathan. I'm going to be talking about approximating the minimum k-edge connected multi-subgraph problem, or KECSM for short. This is joint work with my advisors Anna Karlin and Shayan Oveis Gharan, and a fellow graduate student at the University of Washington, Xinzhi Zhang. All right, so what is KECSM? True to its name, it asks to find a minimum cost spanning multi-subgraph, which is k-edge connected. So I want to choose a multi-set of edges, which k-edge connects the graph. And this multi here refers to the fact that in the subgraph I choose, I'm allowed to take each edge as many times as I'd like. So if this is your graph, this would be a valid solution to 2 ECSM, whereas you can see I've taken this red edge twice. This is a special case of a maybe more well-studied problem, the k-edge connected spanning subgraph problem, so without the multi, where the only difference is that I'm not allowed to take an edge more than once. So this would not be a valid 2ECSS solution. KECSM is NP hard, so we're going to study approximation algorithms for it. These are procedures which run quickly and return a solution whose cost is provably within some hopefully small factor of the optimal solution. Here's a quick summary of what was known about the problem. For comparison, we'll also look at this more general problem, KECSS. In KECSM, in the weighted case, basically the best known was a 3/2 approximation. In other words, an algorithm which runs quickly and whose solution never costs more than 3/2 times the cost of the optimum solution. And this result pretty much followed from Christophidis' algorithm for TSP. We also have an approximation algorithm which can be much better, but only when k is at least log n. So this is from Karger in the late 90s. And it works by observing that when k is so large, if we take the support of a solution x to the natural LP relaxation for the problem, which I'll tell you about in a second, so if we take such a solution x, and then sample every edge independently with probability xe, then with high probability, the graph is actually close to k-edge connected already. And all you need to do is add a few extra spanning trees to fix up the graph. For comparison, in KECSS, we only know a 2 approximation due to Jane's iterative rounding framework. And a major open question is whether we can beat an approximation factor of 2 for any k. One interesting property of these problems is that the unweighted case is comparatively easier, at least as k grows. So for both problems, we have a 1 + 2 over k approximation for the unweighted case. In other words, the setting where I want to get a k-edge connected subgraph using the fewest number of edges possible. And so one thing you might ask is whether you can get such great guarantees for the weighted case as well. However, for KECSS, we know this is not possible. There's a proven separation between the weighted and the unweighted case. So here this is APX hard for all k, and here the ratio goes to 1. There's really fundamentally something different that happens when you are allowed to add weights in KECSS. Now I want to clarify that when I say APX hard for all k, I mean there's a single constant epsilon such that there's no better than 1 + epsilon approximation for any k. So this kind of result is therefore not possible. But for KECSM, there's no similar lower bound for the weighted case. We only know that it's NP hard for general k and APX hard for k = 2. Therefore, for KECSM, there's some hope that the weighted case could actually get easier as k gets larger. Karger's result already gives us some partial progress for this question, but only when k is a function of n, which we may not have. So kind of seeing this situation after proving these two results, Pritchard conjectured that there's a 1 + order 1 over k approximation for weighted KECSM, so matching the unweighted case asymptotically. Now, we tried, but we couldn't prove it. So what do? Let's make a weaker version of this conjecture. Maybe let's first just figure out if there's an approximation algorithm whose ratio goes to 1 as k grows, independent of n. In other words, can we rule out that it's APX hard for all k? And this we were able to prove. So we showed that there's a 1 plus order 1 over square root k approximation algorithm for the problem, which proves this weaker conjecture. The constant here isn't so bad, it's about 5. So this becomes better than 3/2 for sort of modest-ish values of k. One can also compare it to Karger's algorithm. We kind of remove the log n factor. So here's a roadmap for the rest of the talk. I'll start with some basic polyhedral background and give you the main idea of the algorithm. The algorithm will rely on sampling spanning trees, which have some concentration properties. And we'll use so-called lambda uniform or max entropy distributions to achieve that, which I'll talk very briefly about. And finally, I'll explain an algorithm with a factor that's just a tiny bit worse than what I claim. So we'll get an additional square root log k. All right, so let's start with the polyhedral background. So to approach this problem, we'll start with its linear programming relaxation, which I'll call the k-edge connectivity LP. It just asks for fraction k to go across every cut. So it's asking for a fractionally k-edge connected graph. For example, here's a solution for k equals 2. And notice that since we allow edges to be used more than once, there's actually an underlying metric. If I want to use an edge from, say, u to v, I can always instead use the edges from u to w and w to v. I get the same connectivity by doing that. Therefore, I get the triangle inequality. Having this metric implies that every vertex will have degree exactly k in any extreme point solution by what's known as the parsimonious property. And so one can see that if k equals 2, this is exactly the held Karp relaxation for TSP. So this polytope, at least for k equals 2, has some history. And actually, there's something quite nice about the 2 connectivity polytope. It turns out that this polytope is actually contained in the spanning tree polytope up to some tiny discrepancy we're not going to worry about. So whenever I get a point x in the 2 connectivity polytope, I can simply place it in the spanning tree polytope. And in general, if we solve the k connectivity LP and get a point x, we can scale it down and just following these arrows, obtain x is equal to k over 2 times the point z in the spanning tree polytope. So the upshot is that if we have a solution x to this connectivity LP, we can use it to sample a tree which costs only 2 over k times the cost of x in expectation. And since I'm allowed to use edges any number of times, I can sample as many trees from this distribution as I want, sort of independently, and take their disjoint union. And for some of you, this may already be kind of suggestive, so you may be able to guess some of the next slide already. So now the algorithm is the following. Let x be a solution to the k connectivity LP. Now let's transform it using the last slide into k over 2 times the point z in the spanning tree polytope. Now let's sample k over 2 plus 1 trees independently from some nice distribution mu with over spanning trees with marginal z, which I'll talk about shortly. The only thing I'm going to use in this talk about mu is that it has nice concentration properties. So among any set of edges, the number of edges that appear in a random tree should be tightly concentrated around its expectation. It turns out that to get rid of the log and the approximation factor, we end up using some other properties of mu. So if you're interested in that, you can check out the paper. But actually, for this talk, there are several choices for mu that would work, such as Chakuri and Von Dreck's randomized pipage rounding, or Chakuri, Von Dreck, and Zinclusen swap rounding. And I'll tell you about the one we use to get the tighter factor, called max entropy sampling. But yeah, for this talk, feel free to pick your favorite. Now let T star be the disjoint union of these trees. This is not quite a solution, right? We're going to have to patch up the cuts, which have fewer than k edges in T star. But basically, step 4 is to somehow do this in a way which is not too expensive. And intuitively, you may expect it should be fairly cheap to fix T star as K gets large. We expect to have at least K edges across every cut because X is fractionally K edge connected, and just K over 2 trees will already give you the marginals of X. And due to concentration, it's going to be unlikely that we get fewer than K minus some lower order term number of edges in any cut. The issue is, of course, that kind of a priori, we have to worry about 2 to the n cuts. And this is basically the reason that Karger's algorithm has a log n and not a log k. He kind of union bounds over all cuts, but we'll manage to get around this. Before we talk about step 4, though, I'll just briefly introduce the tree distribution mu we'll be using. We'll use so-called lambda uniform tree distributions. So we say a spanning tree distribution is lambda uniform if every edge has weight lambda e, and the probability of a spanning tree is proportional to the product of the lambda e's in its edge set. So for example, this graph with lambdas 3/4, 1/2, and 1/2 would yield the following distribution over spanning trees. And it was proved in 2010 by Sadpour et al. That for any point x in the spanning tree polytope, we can find weights lambda in polynomial time such that the resulting lambda uniform spanning tree distribution matches the marginals of x. And they do so using a so-called max entropy convex program, hence the name max entropy. And in a sense, you can think of lambda uniform trees as a kind of scaling of uniformly random trees, for which we would have lambda e equals 1 for all edges. So you should expect some of the desirable properties of uniformly random trees to carry over. And indeed they do. The fact we'll use is that max entropy trees have strong concentration properties. In particular, any set of edges obeys standard Chernoff bounds. Using this, it's straightforward to obtain the following corollary. Consider a max entropy distribution mu with marginals from our scaled down K edge connectivity LP. Then the probability of a particular cut in the union of K over 2 trees drawn from mu has fewer than K minus square root K log K edges is at most 1 over square root K. So all I'm doing is setting epsilon equal to square root log K over K and Q to be K, which I can do since every cut has fraction at least K crossing it in the LP, and hence in the marginals of the union of K over 2 trees. Notice I put T star star here to distinguish it from the T star in our algorithm, which is actually K over 2 plus 1 trees. And we do this because now, even if you leave one tree out from T star, there are at least this many edges across any fixed cut with high probability. In other words, the K over 2 trees that remain, leaving this one tree out, still have the same marginals as X. Of course, there's something particularly special about sampling K over 2 plus 1 trees. It'll just make the analysis a little bit more transparent. So let's use this concentration to design a good algorithm. As a reminder, this is the algorithm framework. I'm going to tell you now about step 4. So as a thought experiment, imagine that K equals 4 and I sample these 2 trees. So think about the K over 2 plus 1. The 1 is kind of an extra tree. I won't talk about it right now. And now let's look at the union of these 2 trees. Now it's not hard to see that the only cuts I need to worry about, which in this case are these ones, must have exactly one edge in at least one of the trees. So that's a very innocent observation. If a cut has at least 2 edges in both T1 and T2, then the cut has at least 4 edges and I'm fine. This immediately tells me that I need not worry about more than 2 times n minus 1 cuts or order K times n cuts in general, as this is the maximum number of possible cuts with only one edge in some spanning tree. So while it's true that kind of before sampling, I'm worried about all 2 to the n cuts, kind of after sampling, the only cuts I need to check, the number of cuts I need to check is at most order of K times n. And if we personify these bad cuts for a moment, we can imagine that they might blame the trees which have only one edge across them. So this cut might get mad at this tree, and maybe in particular this edge, sort of why are you the only edge across this cut in this tree? Maybe this cut will get mad at this edge, and maybe this cut here mad at both of these edges. And let's work with the intuition that we blame the trees which had exactly one edge across the cut. And in fact, we blame the set of edges which are alone across this cut in their respective tree. I know it's really like the fault of the edges that didn't appear, but sort of these are the ones that showed up, and so they'll have to take the fall. And now what's the natural thing to do? Well, if it's this set of edges' fault, we can look at any bad cut, so any cut with fewer than k edges, and just add an additional copy of the edges that we blamed. In this way, for any bad cut, we'll fix it by making sure that actually every tree has at least 2 edges in the cut. So it's at least k after this process. So this does actually work in the sense that it makes the graph k edge connected. But it turns out it's not a very good approximation algorithm. Basically, this is because if you fix an edge of t star, it's going to double sort of over the randomness of the remaining trees. It's going to double unless the rest of the trees have a total of at least k minus 1 edges in this cut. But the probability that happens could actually be quite large, maybe as large as 1/2. And in that case, you're going to end up doubling an edge with a very high probability. And so this step will be very expensive, maybe leading to a 3/2 approximation. Okay. So we want to try to avoid this. How do we fix this problem? First, we're going to add square root of k log k spanning trees to the solution. That number might ring a bell. And then we're going to do exactly the same thing. So now I'll say a cut is bad. Instead of a cut is bad, meaning it has fewer than k edges, it's bad if it has fewer than k minus square root k log k edges. So those with more than this number are fixed by these extra trees. So now let's see what chance we have of doubling an edge. So condition on a tree ti and an edge e in that tree, which induces the cut c, as in this picture. So c is the unique cut in ti that contains exactly the edge e. Then we double e if the other k over 2 trees end up having fewer than k minus square root k log k edges in that cut. And remember that these trees are sampled independently of ti. Okay, but this again looks familiar. We already know the probability that this occurs. It's at most 1 over square root k due to the concentration properties of our lambda uniform trees and the fact that there are k over 2 other trees in t star. Therefore, conditioned on an edge e appearing in tree ti, it's doubled in t star at the end of this process with probability at most 1 over square root k. This implies that the cost of the doubling step is only 1 over square root k times the cost of the LP in expectation. And that gives us our desired result. And actually, I'll go over this a little bit more carefully in a couple of slides. But first, I want to just show the algorithm again written out, where kind of here is the fixing procedure. And you can see that's actually very straightforward. After sampling these trees and adding a few extra ones, you can just loop over all n times k edges in t star and double the edge if that cut is too small. So that's the whole process. Now here's the analysis again, said slightly more formally. So first we sample k over 2 plus 1 trees. This costs a tiny bit more than opt, which we won't worry about. Let's say it costs opt. And then we add an additional square root k log k trees, which since every tree costs 2 over k times the cost of opt, costs this much. So this is the dominating term. And finally, we need to argue that the cost of the doubling step is not too high. And as long as we do this, we get the desired ratio. And you can see that the constant is not too bad. So let's do the analysis a little bit more carefully. So for an edge E in Ti, let C of E sub I be the unique cut S for which delta S intersect T is exactly E. And now let's calculate the expected number of times we double E across the whole procedure. As long as this is going to be a 1 over square root k factor times xe, we're going to be done. So let's calculate this. So for each of the k over 2 plus 1 sampled trees, we have some chance to double the edge in that tree. So first we check if the edge is in Ti. Now, if it is, we see if this copy of the edge is going to be doubled. Remember, we treat each copy of E and each Ti independently. The probability it's doubled is the probability that T star has fewer than k minus square root of k log k edges across the cut. Now, ignoring Ti, this is upper bounded by the probability that the remaining k over 2 independently sampled trees have fewer than this number of edges across the cut. But this is exactly our corollary. The k over 2 edges have at least k edges across CE sub I in expectation. So the probability they have fewer than this is, as we said, at most 1 over square root k. And plugging this all in and ignoring this plus 1 here, this is equal to 1 over square root k times xe as desired. Okay, so there are several open questions now that appear approachable. The first is proving Pritchard's 1 over k conjecture, or kind of in another direction, getting substantially better than 3/2 for 2 ECSM. So the best known for 2 ECSM is 3/2 minus epsilon for some very small epsilon. And I'll note that to get this factor of 1 plus order 1 over k, the algorithm we propose does not work. What we prove is tight up to the constant in the 1 over square root k term. The second open question is whether we can get a similar result for the directed k-edge connectivity problem, where we're again allowed to use edges more than once. So this is not known, and actually our techniques seem to break down completely in the directed case. And finally, as far as we're aware, there's no result showing that KECSM is hard to approximate better than 1 over omega of 1 over k. And this is conjectured in Pritchard's paper as well, and we kind of strongly believe this should be true. Okay, so thanks so much for listening.